Okay, so welcome. Today we're going to be talking about the electric field around a charge. Really to answer the question, how can two things that are not touching experience a force on each other? So here we want to first start talking about this concept of action at a distance. Objects not in contact, they experience a force. Now we have seen this with the force of gravity. That the force of gravity doesn't need to have two things physically touching in order to feel a tug on each other. So the question is, what's the problem with that? Why can't things that are not touching experience a force? The question really becomes, what is the mechanism? So what is the mechanism for us in order to explain how this works? So the solution to that is that rather than thinking about the objects touching physically, we can say that objects are in constant contact with a field. Okay, so just like we discussed with a gravitational field, we have an electric field when we're talking about electric forces. So what is it? It's really described as an alteration of space around charge A that is the agent, in other words, the thing that's causing the agent that exerts a force on charge B. So if we have these two charges, doesn't matter what their sign is, charge A and charge B, that charge A exerts this alteration of space around charge B to let charge B know that it's there. So we can say that there's a force on due to A on B, and then there's a force from this one that is from B on A. And that's kind of a nice example of Newton's third law. So then what are the two components of all fields? All fields have both magnitude and direction, making it a vector. Okay, it's really important to realize that electric fields are vectors. So then how are the fields represented? Well, we draw these electric field lines. And then how is the shape determined? Well, we need something that is going to be our fly on the wall. It's something that can detect the force field without altering. So we think of a probe that is a positive test charge. And this is going to be our basis. I'm going to actually use the symbol Q sub t for just test charge. And that's going to be our idea. Just when you're drawing electric field lines, think of which way would a positive charge move. So the question then becomes, how are the field lines drawn around a single positively charged? So if I have just a positively charged object here and a single negatively charged object here. So if I put my little test charge here, what way would it move? Well, of course that the positive charge would repel this positive charge. So that positive charge would move up and away. If I move my positive charge over here, it would still move up and away from it. If the positive test charge is over here, it would move out and away. And then so what we end up getting is that if we think of our test charge around in all the directions, it's going to be moving out and away in all cases. Now, around a negatively charged object, if I put my positive test charge out here, the positive test charge and the negative charge are going to attract to each other. So this one would move towards the negative. If I put a test charge over here, it's going to move towards the negative. Okay, and the same thing goes for in all directions. So the field lines around a positive charge and a negative charge look the same, with the exception that they point in opposite directions. So this is how we'd represent the electric field around a negative charge. This is how we'd represent the electric field around a positive charge. So how can we show a strong electric field? Okay, it's not that we would draw in longer field lines. We would draw in more field lines. So if we add in more field lines, we can get an idea of how strong that electric field. So let's say this is 3 times the charge. Well, it's going to have, and it's positive so the field lines are going to go away. So it's going to have 3 times the field lines. And they all go radially away from the center. And so we can kind of look at different regions in space. If I want to kind of concentrate on this region right here in yellow, and then this region, I'm going to choose a region right here in blue. Notice that in the blue, the 2 field lines are closer together. So what we would actually say is that right here, and actually, I'm sorry, I'm going to do this in a different color. Right here, it's a strong field since the lines are closer together, and then right here, it is a weaker field since the field lines are further apart. Okay, so we can tell kind of an idea of where the field is strongest, and this makes sense that the field is stronger when it's closer to the charge, that it gets weaker with distance. Now, we don't know at the moment of how that varies, but you might be able to kind of put 2 and 2 together. So note the length of the field lines does not indicate anything about the field strength. Don't just simply draw longer field lines in order to show a stronger field. So the question now becomes, what does it look like if we have combination of charges? Okay, so this gets a little bit more complex. So let's say we have a positive charge here and a negative charge there, and then we have 2 positives over here. So this over here is one situation, and this over here is one situation. So here's what I could think of, that if I put a positive charge here, it's going to be repelling this positive charge, but it's also going to be attracting this negative charge. So if I kind of think of it, if I track it from here to here, it's going to be moving away, and then it's going to dip down towards the negative. So it's going to be following this path simply because that as it gets further away from the positive, it's going to want to be attracted down towards the negative. So the negative pulls on it harder when it's closer to it. If I put it right in the center, it's going to just go straight along, and we have kind of this nice symmetrical argument over here. And then the same thing goes in all directions. What we'd end up seeing is that we see the field line leave the positive, come out and around, and come back in towards the negative. Now, generally speaking, we won't show the entire semicircle, okay, but we can certainly get an idea for what it looks like. Okay, now on the positive, if I place a positive charge, let's say right here, well, it's going to want to repel this one on the left here, but it's also going to want to repel this one. So as it gets further away from the one on the left, it's also repelling the one on the right, so the field line is going to look something like that. Over here, the same thing, and notice that the 2 fields are kind of pushing off one another. Down over here, if I put a positive charge here, it's going to want to get away from the one on the left. If I put a positive charge right here, it's going to want to get away from the one on the right. And notice that I'm not crossing these field lines. It actually goes that the field lines will never cross. So I can continue this in all directions around. Okay, so our field lines look something like so. Okay. Now this would be the same kind of symmetry for negative negative. The only difference is all the field lines would point inward instead of outward. All right. So of the 5 examples, is the field uniform in magnitude and direction? Okay. Now notice that anytime that you have a curved line, okay, that's not uniform in direction. Right here it's kind of pointing out and away in this direction. Right here it's pointing that way, and this would continue to curve. So definitely no to the direction. And then also, as we said earlier, it's also not constant in magnitude. We kind of get this idea that as the field lines get further and further apart, it gets weaker. So this is a no. Okay, so how can we make a uniform field? Well, if we have 2 parallel plates and we charge one negative, let's say we strip electrons off the top plate, making it positive, and deposit them on the bottom plate, making it negative, then what we'd end up getting is this nice uniform field. So we call these parallel plates, okay, for kind of obvious reasons. And they create this nice uniform electric field. So the electric field in here goes away from the positive. Think about which way a positive test charge would move. Away from the positive, and it tracks towards the negative. So we have these nice uniform field lines. So I'm going to try to keep them as close to equal distance apart as I can. And then towards the edges, it gets a little less uniform, kind of bends away, and then comes towards back the negative. So I'm going to show a little bit of a bending on the left and right side. And we have 2 electrons. So notice that the electrons are, E1 is closer than E2. But the important thing is that they are in this uniform field. Okay, so think about gravity. On Earth, gravity has this nice uniform field, okay, as long as you're not getting too far away from the Earth. So these 2 electrons that are placed between the plates as shown, which particle experiences a greater force? Well, they're in a uniform field. So just like 2 objects, and they have the same charge, right? So 2 objects of equal mass are going to experience the same force on Earth, regardless of whether one is close to the Earth and one is further away. So this is equal. Okay, if electron 2 moved towards the bottom plate, how would that force change? It would not. For the same reason, same argument. For the electrons, how does the direction of the force compare to the direction of the electric field? Okay, notice that the electric field is going down, but the electric force on these charges is going to be moving in the upward direction, because it's going to be attracted towards the positive plate. So the electric field lines go in the opposite direction as the force. So we're going to say that they go opposite to one another. But then the question is, what if we replace this with a proton? A proton, or any positive charge in general, since the electric field lines are drawn in the way that which way a positive test charge would move, the electric field and the electric force for a positive charge go in the same direction. Okay, so it would be the same direction. And like I said, this is not just true for a proton, but it's true for anything that has a positive charge.